Hello, in this video we're going to be looking at the different kinds of calculations that we'll see with titrations outside of just our basic neutralization and finding that equivalence point. This is going to involve calculations that we've all seen before throughout this unit. We're going to see acid, Ka problems, Kb problems, salts, buffer problems, all that stuff. Big thing is just trying to figure out what type of problem are we actually trying to do here, do we need to do. So this is going to be on pages 19 through 22. So we're going to start looking at our strong acid, strong base titrations. There are 3 different places where we're going to need to determine the pH. The first part is when we have just our initial acid concentration. If we only have the strong acid, we just find pH using the negative log of H+. Because it is a strong acid with 100% ionization, H+ is going to equal the concentration of our acid. The second situation where we would need to determine the pH is the equivalence point, and that one's really easy. Once we know we're at the equivalence point, our pH is just going to be 7 because all we have is our neutral salt and water. We can still use MAVA equals MBVB to calculate that equivalence point and the volume we need to reach it. So the one that is a little bit of a new calculation is before and after the equivalence point. So pretty much anywhere on the curve outside of our starting position and that equivalence point. Before and after the equivalence point, we're going to need to do stoichiometry, which we can easily do in a BCA table, and figure out how many moles of H+ or OH- are left over. One of them is going to be in excess. Once we find the concentration by dividing by the total volume, we can just take the negative log of that number to get our pH or our pOH. So let's go through and look at a few examples of this. So we have 100 milliliters of our 1 molar HCl, and we're titrating it with 0.5 molar NaOH. So the first thing we want to know is the pH after 50 milliliters of the base have been added. So I'm not quite sure where that falls on my titration curve. So we can do a stoichiometry in a BCA table to figure that out and figure out our excess. So we do need to start with the reaction that's happening here. Anytime we have a strong acid, we can just denote that using H+. Cl- is just a spectator and we do not care about it. Anytime we have a strong base, we should just denote that using OH-, and in an acid-base in a strong acid, strong base reaction, we're going to be forming that water and the neutral salt, which we don't care about, again, because they're all just spectators. So in our BCA table, remember we always use mole values, or we can use millimoles, which is going to make our life easier in most of these types of problems. So for our millimoles of H+, we have 100 milliliters of 1 molar. Multiply those together, that gives us 100 millimoles. For our millimoles of OH-, we have 50 milliliters of our 0.5 molar. So 50 times 0.5, that's going to be 25 millimoles. We haven't made any water yet. So for that change, we have to find our limiting reactant. Well, there's less OH-, it's going to run out first, it's limiting. All of that OH- is going to get neutralized where there's none left over. But for every 25 millimoles of OH- that react, 25 millimoles of H+ will react, leaving us with 75 millimoles there. Well, in this case, we don't really care about our water, so we can just ignore that guy. We're looking for the pH, which means we need our H+ concentration. Well, I know my millimoles of H+, so to find that H+ concentration, we're going to need to take those millimoles of H+ and divide by the total volume of solution. We had 100 milliliters, and we added 50 milliliters to it. So now our total volume of solution is 150 milliliters. If we keep everything in milliliters like we saw here, Those millis will cancel out, leaving us with 75 divided by 100, which is 0.500 molar. I went back to my 3 sig figs there, kind of going through the millimoles in the BCA table. I didn't keep up with sig figs, but looking back at our problem, 3 sig figs was our least amount of anything that we put into those calculations, so I'm going to round it off to 3 sig figs. Now that we have our H plus concentration, finding the pH is super easy. We're just going to take the negative log of that. And again, keeping those 3 sig figs, that'll give us 0.301 for our pH. So let's go ahead and take a look at part B. Well, again, we can start with that BCA table to figure out where we're at. We still have the same reaction, strong acid plus strong base, making our water. We're still starting with the 100 millimoles of H plus, but now we've added 200 milliliters of base, and our 200 milliliters of base times that 0.5 molar is going to be 100 millimoles as well. Well, we have equal H plus and OH minus. This must be our equivalence point. So since we're at the equivalence point, what do we know our pH is? Oh, our pH must be 7. We're going to add a decimal on here so that we got 3 sig figs. We'll do the same on part C. So 7.000 with our 3 sig figs there. Well, that worked out when we were at the equivalence point. But that's something you can also figure out beforehand as well, if that helps you with the problem. And it's certainly something that I would recommend doing on some of these titration problems. If we look at our MAVA equals MBVB beforehand, we can go ahead and determine that equivalence point, so then we can kind of judge our other calculations based on that. If we started with that MAVA equals MBVB before we even did part A, I would find that I need 200 milliliters to get to my equivalence point. And then I would see in part B, oh, that's 200 milliliters. This is my equivalence point, easy, pH of 7. And then I would see part A, okay, that's before my equivalence point. Where before my equivalence point, I'm going to have more moles of H+. That held true. You would still have to do a BCA table to figure out how much. And then in part C, I'd be like, oh, I got 300 milliliters, so I know I must just have OH minus left over. I am past the equivalence point, so now we just have excess base in there. But we have to figure out how much excess base again using that BCA table. So why don't you go ahead and take a try at that BCA table and figure out how much excess base and calculate our pH based off of that. Pause the video and resume when you're ready to check. So on part C, we should find that our pH is 13.097. When we do our BCA table, we still have 100 millimoles of H+, but we have 150 millimoles of our base, our OH minus, that has been added. That leaves us with 50 millimoles of excess OH minus, and now we have to divide by that total volume of 400 milliliters. We have 300 milliliters of base that we added to the 100 milliliters of acid we already have. That gives us the OH minus concentration of 0.125 molar. Negative log of that gives us the POH. Subtract from 14 and we get our pH. Keeping 3 sig figs like we had in that 300 milliliters and a few other numbers throughout. That's our 3 decimal spots on that pH value. So that's when we have strong and strong. So let's go on and look at what happens whenever we have a weak acid titrated with a strong base. Now we have 5 different situations or 5 different types of possible calculations to find the pH at certain points. Well, before our titration begins, we have only a weak acid. Well, we learned this unit how to calculate the pH of a weak acid. We need to do a Rice table and a Ka problem. During the titration, but before our equivalence point, that's our buffer zone. You saw that in the titration curve video. Within that buffer zone, we always have a buffer. As soon as we add our strong base, our weak acid has reacted to form its salt or its conjugate base. That's what a buffer is. Anytime we have a mixture of weak acid and a salt. There is a point where we have that perfect buffer. That perfect buffer ends up at the half equivalence point. That's when half of our weak acid has been reacted with the base and converted into its conjugate A-. If our HA concentration is equal to our A- concentration, at that half equivalence point, it's super easy to find the pH. pH is equal to pKa. So that half equivalence point, really important to know that little trick and to be able to find it. Our fourth place would be at the equivalence point itself. At the equivalence point, our acid and base have completely neutralized each other, and all that's left is a salt and water. However, our salt this time is going to be a basic salt. Because we did a weak acid, strong base titration, so one of the ions of that salt is going to be able to hydrolyze water to form OH-. Well, then we got to do a KB problem in this case to calculate the pH of our basic salt. After the equivalence point, we're just adding excess strong base. So all we need to do is do some stoichiometry, figure out how much excess strong base, and then calculate our pOH from that OH- concentration. So we can see these different points all on a titration curve as well. So again, before the titration has begun, so that's our point number 1 here, we only have a weak acid. That's just a rice table, Ka problem, Ka equals x squared over our initial acid concentration. Immediately after that, anywhere in this buffer zone, so after the initial, before our titration, all the way up to that equivalence point is our second possible type of problem. Well, that's the buffer region. Anywhere in that buffer region, we're going to have a buffer. How do we calculate the pH of a buffer? We use our Henderson-Hasselbalch equation, pH equals pKa plus the log of base over acid. But we need to figure out how much base versus how much acid we have to use that, so we're going to have to do stoichiometry first. That's going to be in the form of our BCA table again. Once we find our concentrations of weak acid and conjugate, we can plug that into Henderson-Hasselbalch. The third point is going to be at that half equivalence point. So we can see here that our equivalence point is at 50 milliliters. So our half equivalence point is 25 milliliters there. Again, it's super important to remember that half equivalence point because it's really easy to find the pH. pH equals pKa. Our fourth stop would be at the equivalence point. At the equivalence point, we only have a basic salt, so that's going to be a KB problem. We'll take the ion from our salt, which will hydrolyze water to form OH- and do our KB from there. After that equivalence point, we're only going to have strong base present. It's the only significant part there. So we need to find the concentration of that strong base using stoich or our BCA table again. And then we can just take the negative log of that concentration to find pOH, subtract from 14 to find pH. The only other type of titration that we have remaining is a weak base plus a strong acid. This is going to be exactly like the weak acid and strong base that we just looked at, but everything is just going to be flip-flopped. Now our first possible location would be when we have weak base only before that titration has begun. Then in this whole entire region here, we're going to have our buffer where we do our stoichiometry to figure out how much acid versus base, plug that into Henderson-Hasselbalch. We still have that super important half equivalence point. So equivalence point was at 50. Half equivalence point is at 25 again. Now, since we have a base, we're probably going to be given pKb. pKb is equal to our pOH, but pKa is still equal to pH at this location as well. So we have a couple different options that we can do to solve that problem. Okay, so then we get to our equivalence point. At the equivalence point, we only have salt again. But this time, it is an acidic salt, so it's going to be a Ka problem. And then lastly, after the equivalence point, we're only going to have strong acid left, so we'll need to do stoichiometry to figure out how much in that H plus concentration, then take the negative log of that. So one more important thing about the half equivalence point, remember, how important it is. After you've determined the equivalence point, again, we know we can always find the half equivalence point because it's half of the volume that you needed to get the equivalence point. At the equivalence point, we know a few things. We know that pH is equal to pKa. But if we know the pH at the half equivalence point and the pKa, we can also find our pKb or our Kb, and you saw this in the titration curve video, so this should not be news. pKb is going to be equal to 14 minus pKa, or pKa plus pKb equals 14. So that's why the other true thing about the half equivalence point is that our POH is going to equal pKb. Alright, so we're going to go through a titration curve problem here, calculating the pH at several different points to see all these different types of calculations. Again, these are all calculations that we've done before in some form or fashion throughout this unit. Alright, so here we're titrating 100 milliliters of 0.2 molar acetic acid with 0.1 molar KOH. We want to know the pH after these following volumes, these 5 different volumes we have here, have been added. One thing that I would recommend on this type of problem is always figuring out where that equivalence point is first. Because once you know your equivalence point, we can kind of figure out whereabouts we're at based on that. So let's do that first, using MAVA equals MBVB. So now that I've done this MAVA equals MBVB real quick here, I see that it's going to take me 200 milliliters to reach the equivalence point. On this one, the math is pretty easy here, so if you figure that out just kind of mentally without actually working out, that is perfectly okay as well. I'm going to keep that in mind because it's going to help me determine where I am in relation to that. Am I at that half equivalence point, etc. Well, the first volume that we're looking at is when we've added 0 milliliters of KOH. If we've added 0 milliliters of KOH, all we have is our acetic acid. This becomes just a Ka problem. Since we just have that acetic acid in water, we're just looking at our weak acid ionization reaction here. We could go through and do our whole rice table. We don't have to. We can go straight to that little shortcut. We know that Ka is equal to our A is equal to our H3O plus times our acetate ion concentration over the whole acid. When we do that in our rice, it's going to be X squared over the initial concentration of our acid minus X. We can still assume that our minus X is negligible because that Ka value is so small, nothing new there. So now we'll set our X squared over initial acid concentration equal to our Ka value, because again, we're doing a Ka problem here. From here, we can go and solve for our X, little cross multiplication and a square root there. So our X is equal to our H3O plus concentration, which is 0.0019 molar. Well, we're looking for the pH. pH is just the negative log of that H3O plus concentration, 0.72. This should not be a new calculation by any means whatsoever. You just have to be able to recognize that we only have a weak acid, so we got to do a Ka problem to calculate its pH. So let's look at part B. So we want to know the volume. It's still the same titration here. Nothing's changed. But now we're looking for the volume after 100 milliliters have been added. Well, Remember back here where we thought about that it's going to take 200 milliliters to reach the equivalence point? Where does that mean my half equivalence point is at? That means my half equivalence point is at this 100 milliliters. And what is so great about the half equivalence point is it makes our life so easy to find the pH. At the half equivalence point, pH is always equal to pKa. pKa is just the negative log of our Ka value, 1.8 times 10 to the negative 5. With our true sig fig still, that would be 4.74. Easy as that. If you don't do that MAV equals MBVB at the beginning and figure out your equivalence point is 200 milliliters and remember, oh hey, my half equivalence point is here at 100 milliliters, we can still stoich it out. So if you were to stoich that out, we're adding strong base, which is just our OH minus, to the acetic acid. That's going to form acetate and water. In millimoles, we have 10 OH minus and 20 acetic acids. We haven't made any product yet. So our change is going to be 10 because that's our limiting reactant for our OH minus. So we're going to lose 10 millimoles of both of our reactants, but we're also going to make 10 millimoles of both of our products. We don't care about the water, but we're going to make 10 millimoles of our acetate ion. We have 10 millimoles of our acetic acid left over. Well, we have equal parts weak acid to our conjugate base. That's our ideal buffer where pH equals pKa. Again, I think it's way easier just to remember where your equivalence point is and recognize that this is your half equivalence point. All right, let's go on and look at part C. Part C, same titration still. Now we're at 150 milliliters. Well, our equivalence point is still at 200 milliliters. So that means that we are somewhere in that buffer zone. We're past the half equivalence point because we just did that. But we have to figure out how much past. How much weak acid versus conjugate base do I have? We can do that using stoichiometry and then go and plug those values into Henderson-Hasselbalch equation. So let's start by looking at the reaction that's going to happen here. We're adding strong base. Again, adding strong base, we only need to put OH minus, ignore those spectators, and we're adding it to weak acid, which stays together. The weak acid is going to neutralize that strong base. Anytime you add something strong, one-way arrow is going to completion. So we're going to form that conjugate base and water in that neutralization. Remember, acids are donating the proton to the base if you don't know what it's making there. So BCA, we can use our millimoles. We have 100 milliliters of 0.2 molar acetic acid. Multiply those together, you get 20 millimoles. Oops, wrong place. 20 millimoles of acetic acid. For our OH minus, we have 0.1 molar times 150. That is 15 milliliters of OH minus, making OH minus our limiting reactant. But if 15 millimoles of OH minus react, so did 15 millimoles of acetic acid. We're left with 5. We also formed 15 millimoles of both of our products, but we don't care about the water. All right. So I see here that, oh hey, I do in fact have a buffer because I have a mixture of weak acid conjugate base. So if we have a buffer, we can use Henderson-Hasselbalch equation. So that's our pH equals pKa plus the log of base over acid. Acetate is our conjugate base and our acid is the weak acetic acid. But we need their concentrations. Right now, what we have is the millimoles. Well, to take our moles and get to concentrations, we need to divide by volume, and we can divide by volume in milliliters. However, we have to remember to divide by the new total volume. That new total volume is 250 milliliters because we had 100 milliliters and we added 150 more. So we've got to divide by that new total volume. That will then give us our concentrations. In those concentrations, we do get to keep 3 sig figs. We had 3 sig figs in all those initial volumes and molarities at least. And now we can take those concentrations and go plug them in to Henderson-Hasselbalch. So when we do that, our pKa is the negative log of the 1.8 times 10 to the negative 5, which is 4.74. We found that earlier in part B if you just wanted to plug that in. Plus the log of concentration of base over acid, that gives us 5.22. We do get to keep 3 sig figs here, so I am missing one. Never mind, that's a lie. We only get 2 sig figs because of that Ka value there of 1.8. Alright, so let's go and look at our next part. For our next part, we're at 200 milliliters. Well, remember, 200 milliliters is our equivalence point. Our equivalence point, we only have our salt and water, but it's a basic salt from the titration of the strong base with a weak acid. We're going to need to do our Kb problem so we can do out our rice table and all here. Well, in our reaction that's happening, we got to know which ion is going to be. The ion that can hydrolyze our water is the ion from the weak parent, which would be our acetate ion. Because that acetate ion hydrolyzes water to form OH-, it's going to be a basic salt. Well, as we go about this, really the only other really important piece of information that I need is that initial acetate ion concentration. So we have to be able to find that. We know our concentration is the moles of acetate over the volume. But we had a volume change, so we need to find our moles of acetate ion and divide by the new total volume. Well, all of the initial acetic acid that I had turned into that acetate ion. I can find how many moles that is. That's 100 milliliters, so volume times molarity, so the 0.20 molar, is going to give us our moles. These number of moles then need to be divided by our total volume. I did keep milliliters up there to find millimoles, so I do want to divide by my total volume in milliliters. That total volume is going to be our 100 milliliters plus 200 milliliters for that 300 milliliters total. Our milliliters will cancel out, giving us moles over liters there. That then will give us a concentration of 0.0667 molar. And again, we get to keep those 3 sig figs. At this point, this problem becomes nothing new. We have the initial concentration of our salt. We can go and plug into our rice table. It is a basic salt producing OH-, so we must do a Kb problem. So after we've plugged that all in, we get our x squared over 0.0667 minus x. X is negligible. This is all equal to our Kb problem. Ooh, we run into a little bit of a snag here. We don't have our Kb value, but that's okay. We can easily find our Kb value from our Ka value. So taking Kw divided by Ka, we get our Kb, which is 5.6 times 10 to the negative 10. Now we can go and solve for x. X is equal to our OH minus concentration. The negative log of that gives us a pOH of 5.21. Subtract from 14 and we get our pH of 8.79. On these problems, it should always be easy enough to ask yourself, does this make sense? Yes, this pH makes sense because we have a basic salt. Our pH should, in fact, be above 7 as we see here. Alright, so we got one more point of our titration left. We're at 250 milliliters. Well, 200 milliliters was my equivalence point, so 250 milliliters were past our equivalence point. The only important thing here is strong base. We just have to figure out how much. We can figure out how much by doing a little stoichiometry again in our BCA table. Strong base, OH minus, reacting with our weak acid to form water and our salt here. We have still 20 millimoles of the weak acid, and now we have 0.1 times 250 or 25 millimoles of OH minus. That leaves our acetic acid as limiting, which we know should be the case because we are past our equivalence point. We do also make 20 millimoles of acetate, and we have 5 OH minus left over. The only thing of importance here is going to be our OH minus. We do not care about that acetate. Because that acetate is a weak base, the OH minus or the H plus from it is insignificant. Kind of like when we have a mixture of acids, only the strongest one matters. This is the exact same thing. We have a mixture of bases, only the strongest one matters. So only that OH minus matters. We're going to use that concentration to find our pH. So let's go ahead and solve for that. 5 millimoles left over, and it is sitting in 100 plus 250 or 350 milliliters, giving us 0.0143 for our OH minus concentration. Taking the negative log of that, OH of 1.84, we do need to subtract from 14 to get our 12. We do still need to subtract from 14 here to get our pH of 12.16. And again, this makes perfect sense. We only have a strong base, so we should have a pH well above 7. There is another similar titration problem on page 23 that I'm going to leave to you to try out. It's the same general process, only big difference is now it's going to be the opposite because we got a weak base, strong acid. But take a look at those, and we'll be practicing more with titration curves, plus all these titration calculations in class next time.